Okay, the capacitor for option 2, electronics and control, the question with the 555 timer, they ask you about timing and frequency. That's all got to do with the capacitor. So the capacitor has units called farads, named after Michael Faraday. Some of them are polarized, which means that they have one longer leg than the other. So you must go into the circuit with the anode and the cathode in the right direction. And some of them are non-polarized. Okay, so they have legs the same length. Remember before, the capacitor stores an electric charge within two metal plates inside the capacitor. Okay, that area is called the electric field, and it stores a charge which is waiting for discharge. Now let's have a closer look at a previous circuit which we've looked at and talked about. Okay, yeah, so here's a 555 timer, just like you would see in the exam. Here's our potential divider input area, which controls the timing of our outputs over here, our LEDs on pin 3. So let's have a look at the output and what happens when our circuit is on. Okay, so just put a new probe on here, and we will run the circuit now. Okay, yeah, so we see we got a 6-volt output and then a sharp drop, and 6-volt output, sharp drop. So we have current sourcing out and sinking in here, just like we've seen before. And we got a square output wave form here. Okay. Also note that the first wave output takes a little bit longer than the other ones. Okay. So there's a longer output than this one. That's because the capacitor, the first time when a circuit is on, takes a little bit longer to charge up, and then after that it never fully discharges, and that's why it becomes more uniform after that. Now let's look what happens and see when we change the values across here. So we look at a simpler circuit. Wrong one. There we go. So a transistor circuit with a simpler potential divider here and a capacitor here for charging. All right, so actually I'm just going to make this smaller to begin with. So we have 1,000 microfarads in our circuit to help us control the LED output here. So let's run it here. Okay, 1, 2, 3. So roughly 3 seconds to get our LED on. Okay, so let's see what's happening in the circuit. Okay, so when the circuit comes on, our voltage, travels along here. The transistor is not on, so it has nowhere to go. So our voltage flows down this way, and our capacitor is like a bucket. It is waiting there, ready for charging. So the voltage will go into this electric field in between the two plates, and it builds up like a bucket of water. When it gets to a certain level, then the voltage can flow down here towards the base of our transistor. And when the voltage at this point gets to a certain level that our transistor likes, it opens up like a switch and then allows the LED to come on here. Now, so that took about 3 seconds. Let's watch what happens if we change the value of our transistor. Oh, capacitor. It's a bigger capacitor now, so it should take a little bit longer now. There we go. So it took almost twice as long, I reckon. Let's stop our circuit again. Okay. And we'll empty our capacitor completely. and then we'll run it again. And this time we'll watch our voltage, because remember the voltage has to be at a certain point for our transistor to switch on. So let's watch that now. So 2 volts, 2 points. So in around 2.5 volts there, our LED started to light up. Okay. Now also watch what happens when I switch the circuit off. Okay. So our LED, watch that. Still on, and then goes off. Because what's happening is the capacitor is discharging and our LED is sourcing current from our capacitor, even though our circuit is open. But yeah, that's what's happening. Okay, so you might see that on cars, where there's a safety thing built into the cars where the lights are timed to stay on to help people get into their houses when it's dark. That's one example of where you might see it. Now, we can also change the timing of our output for our circuit by changing the value of our resistor. With this circuit here, with this calculation here, where the timing is equal to the capacitance times the resistance. All right. We can change the circuit around and say if we're looking for a resistance or the resistor size, we can say that R is equal to the timing divided by the capacitance. Okay. So we can say R is equal to T divided by C. That's one way to change the timing of our circuit. Okay. And for finding the resistor size. Now, they can also ask you for the frequency. Okay, so let's have a look at a question in relation to the frequency. 2019, yeah. So in 2019, they said calculate the frequency f in hertz. So hertz is our unit of timing here. Okay, the frequency f in hertz of the astable output. So of our output here, which would be connected to an LED, more than likely, if the value of the capacitance is 10 microfarads, so that's 10 millionths of a farad, all right, and R1 is equal to 2 kilo ohms and R2 is equal to 39 kilo ohms, where 2 kilo ohms is 1,000 ohms and R2 is 39,000 ohms. So we convert these to their base units. So this would be 10 millionths, so that'd be like 0.050, 0.00001, all right, farads, and this would be 2,000 and 39,000. And when you work it out, you get, where's the answer gone? Sorry, 2019. What did I do there? Show market, right, I didn't click it right. There we go. So it's 2,000 plus 2 times 39,000 multiplied by 0.0000345 and one more because it's 10. So there's our 6 zeros. So 10 millionths of a farad. Okay, so it's 2,000 plus 78,000 multiplied by this gives us 0.8. So 1.4 divided by 0.8 will give us the answer that we're looking for, 1.8 hertz. That's our timing frequency. So that's how we change the timing. That's 2 ways to change the timing: by changing the resistance, changing the size of the capacitor, and we can also work out the timing frequency with this formula here. All got to do with capacitors and the 555 timing chip.